Okay, year 11, let's have a look at your paper 4. So I've already written the answers out to hopefully speed this video up a little bit. So we've got in question 1, figure 1.1 shows a distance time graph for a cyclist travelling between points P and V on a straight road. So the first thing I would do is I'd look at what has been plotted. It's distance against time. Distance divided by time is the gradient, and that means that the speed is the gradient of the graph. And so it then says, describe the motion between Q and R and S and T. So, if I take my ruler, you can hopefully see that between Q and R, my gradient is constant. Because I have a constant gradient and the speed is the gradient, I must have constant speed between Q and R. Between R and S, hopefully you can see that the gradient, if I take the tangent to the curve, it's decreasing. So, therefore, because the gradient is decreasing, the speed is decreasing. Then, between S and T, hopefully it's pretty obvious to you. The distance hasn't changed the whole way, so we can't be moving, so we're stationary. Then it asks you to calculate the speed between U and V. We've said that the speed is the gradient, so we're going to find the change in Y over the change in X between U and V, so that's important that we get the right part of the graph. So, you can see between U and V, I've drawn my triangle. This change in time is 100 seconds, it's between 300 and 400, and the change in speed is between 440 here and 600, so that's a difference of 160 metres. So I then do my 160 metre change in Y divided by my 100 second change in X, and I get a speed of 1.6 metres per second. Okay. Then it says, after point V, the straight road continues down a steep hill. The cyclist travels down the steep hill, does not apply the brakes, and all resistive forces can be ignored, so there's no friction. So hopefully you've all ridden a bike or you've gone down a hill in some form. You know that if you don't apply the brakes, you speed up because you're accelerating due to gravity. So the speed is increasing. So therefore, because the gradient of the graph is speed, as I've said 100 times, the gradient also has to increase. So all you need to do is add a section from V where you've got a line that gets an increase in gradient, so getting steeper. And that will get you the 1 mark there. In question 2, which is about gas pressure, it says, state what happens to the molecules of a gas in a sealed container when the temperature of the gas is increased. Well, if the temperature has increased, the average kinetic energy of the molecules has gone up. So, heat has been transferred to kinetic energy of the molecules gain kinetic energy, and therefore they move faster. A quantity of gas is contained in a sealed container of fixed volume. The temperature of the gas is increased. State in terms of molecules 2 reasons why the pressure increases. So, help yourself out. Write the equation. Pressure is force over area. As molecular speed is increased, which we've said happens because they've gained kinetic energy, that means that every time they hit the wall, because they're hitting it faster, they will hit it with more force. You would far rather you bumped into someone that was walking compared to someone that was running, right? It would hurt less. As molecular speed is increased, they hit the wall with more force, and additionally, there's more force in total, because if they're bouncing around faster, they're going to hit the container walls more frequently. So in the same amount of time, there will be more collisions, meaning more overall force acting on the same area. Okay, so it's about the size of the force and the number of collisions. In part C, we have a helium-filled weather balloon held at ground level. The volume was 4,800 metres cubed and the pressure was 98 kilopascals. Don't forget that that means multiplied by 1,000. The balloon is released and rises to a height where the volume is 7,200. Calculate the new pressure of the helium, assuming that the temperature stays constant. So we know that PV is constant when the temperature remains the same. So P1 multiplied by V1 equals P2 multiplied by V2. We have the pressure and the volume before. We don't know the pressure afterwards, but we are told the volume afterwards. all I do is I rearrange this equation here to get P2, and I get 65,333 pascals. And then lastly it says, suggest why helium from the balloon as it rises even higher. So obviously as it rises higher, we know that the pressure inside the balloon is going to be bigger compared to the outside, because outside, as you go up, there's less air. And so the difference between the pressure inside, which is high, and the pressure outside, causes there to be a very high chance of the balloon bursting. So you just want to say, to prevent the balloon from bursting, so that the pressure doesn't cause it to burst. And if you release some of the helium, you're removing some of that air, you're reducing the pressure. So in question 3, alright, so you can see it, we've got a cliff edge with a ball on the top. The ball falls over the edge of the cliff. The mass of the ball is 160 grams. Careful, that's the kind of thing that can trip you up. Convert it into kilograms so that your equations work. The height of the cliff is 115 meters. Calculate the vertical speed of the ball as it hits the water. Air resistance can be ignored. Now, they don't tell you this for no reason. If there's no air resistance, there's no energy lost to the surroundings because of friction. So all of the potential energy that the ball has at the top can be converted to kinetic energy at the bottom. So at the top it has mgh, gravitational potential energy. At the bottom it's lost that, but it's transferred it to the kinetic energy, which is a half mv squared. And we know that they must be equal to each other. The m's cancel from both sides of the equation. I pull my 2 up and I square root so that v is equal to root 2gh. I plug my numbers in because 2 is just 2, g is 10, and the height is 115 meters, and I get a value of 48 meters per second. In part B, it asks you to calculate the vertical momentum of the ball as it hits the water. Well, as it hits the water, we've just worked out that it's travelling at 48 meters per second, okay, and then it will slow down to rest when it hits the water. But at the instant that it hits, it's at 48 meters per second. Momentum is mass multiplied by velocity. The mass, remember, in kilograms is 0.16. The velocity is 48, and when you plug that in, you get 7.7 kilogram meters per second. 4a, define power. This was done very badly, actually. I was surprised. So, power is energy transferred per unit time. Lots of you were writing things like over an amount of time. It was very vague. Try and be very specific. It's 5 words. It's really easy to just memorize. So please just make sure that you take some time to read the equations and definitions list that I gave you and learn them off by heart. In part II, it asks you to tick the boxes to calculate the work done. Write your equation. Lots of you not writing things down and leaving it in your head is going to cause things to go wrong. So work done is force times distance. So therefore, you just tick force and you tick distance. In B, a lift, which is an elevator, in a high building transports 12 passengers, each of mass 65 kilograms, through a vertical height of 150 meters in 64 seconds. Now, the total mass is the first thing I'm even thinking about because I've got 12 passengers. They're each 65, so in total I've got 780 kilograms. You get a mark for that. Calculate the power needed to transport the passengers through this height. Well, power, we've defined, is energy divided by time. It's the energy transferred per unit time. The energy transferred to lift passengers up must be that they gain gravitational potential energy. So E is equal to mgh. The mass of the passengers in total is 780. G is just 10. The height they are moving through is 150 meters. And they do that in 64 seconds. It's just plugging the numbers in. And when you plug that all in, you get 18,281 watts, or 1.8 kilowatts if you've rounded that off. I will give you the marks either way. Okay, so it's 1 mark for this bit, 1 mark for working this out, 1 mark for plugging it in, and 1 mark for your final answer. In part II, The lift is driven by an electric motor. State a reason other than friction. So you can't talk about energy loss to the surroundings because that's already been explained. Why the power supplied by the motor is actually greater than the power that you've just worked out. So this was needed to lift the passengers, but it still requires power to lift the elevator in itself. It's heavy. Okay, so you just need to say energy is required to raise the mass of the lift itself. Okay, this was a nasty question because it was 5 marks, but some of you are not reading your questions carefully enough. And you're missing out, even though your physics is good, you're not using the language that you need to. So you've got a cross-section of a vacuum flask. It contains a cold liquid. It's not hot. Okay, so sometimes you use these flasks for hot liquids, but in this case, the heat is outside and the liquid itself is cold. Okay, and we know that heat will always go from a higher temperature object to a lower temperature object. So we're trying to prevent heat from getting in. What I've done is I've numbered the different parts that I'm going to talk about because I can see it's worth 5 marks, and if I don't structure my answer, something's going to go wrong. So the vacuum flask is being used to keep a liquid cool on a hot day. Explain how the labelled features, which I've numbered now to help myself, will keep the liquid cool by reducing thermal energy transfer. And this was the bit that lots of you missed. Include the names of the processes involved. If you don't use the words conduction, convection and radiation, which are the heat transfer processes, you're not going to get the marks. So, number 1 was the stopper. Clearly, heat in the air would be getting in via a convection current. Okay, it's a fluid, and we know that heat transfer in gas will be through convection. So we say the stopper prevents heat gain by convection. 1 mark. The second one is from the silvered surfaces. Okay, there's actually 2 marks available here. 1 mark for referencing radiation being linked to the silver bit, and the second mark for saying that silver is either a poor absorber or a good reflector of radiation. Okay, so 1 mark for the reference of radiation, 1 mark for referencing that silver is good at reflecting it away but not good at absorbing it in. Number 3 is the vacuum. A vacuum contains no molecules. That's what a vacuum is, it's empty space. Conduction and convection are heat transfer methods with particles. You have to have particles to have convection and conduction. So therefore a vacuum contains no molecules and so prevents heat transfer by conduction and convection. And then last but not least, glass. Really straightforward. Glass is a poor conductor. Okay, and so that gets you your 5 marks. Each one's worth 1 except for the one about silver where you get 2. And then it says, suggest a suitable material for the stopper. Well, if we're trying to keep things cool, we need this to prevent heat transfer in, so we need it to be an insulator. So therefore rubber, cork, wood, plastic, that kind of thing, anything that's insulating would have got you a mark. Okay, 6A, you've got a water wave in a ripple tank. It's clearly travelling in, hits a boundary, and it then travels off in a new direction. You just need to remember that if a wave changes direction because it changes speed, that is called refraction. And the cause for the change in direction is by saying that the wave speed changes, and in this case it's because the water depth changes. But remember, for any wave with refraction, it might not be due to a water wave, it could be a different kind of wave. Refraction, change in direction, comes from saying that the water speed has changed. Okay, this one next was not done well at all. You guys need to take more care of your diagrams. So we've got a transverse wave, and it asks you to draw a wave which has half the amplitude and a greater frequency. So I literally measured this distance with a ruler, and I halved that distance because the amplitude is the total height from equilibrium. And so I marked out where I needed to get to. You guys were all over the place doing things like this. It looked really silly for some of you. So just be careful. Maybe you ran out of time. But mark it out. There's no problem with doing that. And that way you're going to get a nice diagram. Okay, to make my life easy, I just fitted a whole wave inside of a half wavelength, and that way I knew that I was keeping a consistent frequency and it was higher. Okay, obviously you would have got a mark if you'd have done a very thin, that's a bad use of language, a very small wavelength. That would have been fine, but this is just the easiest way I can suggest to you so that you get all of your marks. In C, a train travels along steel rails. A person waiting at the station hears the sound of the train through the rails before he hears the sound through the air. Explain why this happens. Well, it's just a simple case of saying that sound travels faster in solids compared to gases. 1 mark. And then it asks you to calculate the wavelength of sound. So we rearrange our wave speed equation. Wavelength is wave speed divided by frequency. We're told that the speed is 5,800 and we're told that the frequency is 1,100. Plug it into your calculator and you'll get your wavelength of 5.3 meters. Another definition here. This again wasn't done too well. We need to learn our definitions. State what is meant by frequency. The number of waves passing a point per second. Done. Okay, the sound wave travels in air towards a barrier with a small gap at its centre. So you can see that the gap is very similar to the wavelength size, and that's optimal for diffraction. So we're going to get very good diffraction. Okay, I'm actually skipping a bit, but we'll look at it because the diagram is next. So later on it asks you to draw the pattern of compressions, which just means show your wavefronts after the sound has passed through the gap. Okay, so you're just drawing your diffraction pattern. Please be careful, the wavelength needs to remain quite similar. It doesn't have to be perfect because obviously it's a circle, but if you've got something like this, that's no good because this is clearly much smaller than this. Okay, so just be careful there. And what is meant by a compression is a region of high pressure or where particles are closer together. Okay, that's just your definition there as well. And then last but not least on this question then, the barrier is adjusted so that the gap becomes wider. So I've sketched it here, so the gap is now very big compared to the wavelength, which means there will not be much diffraction. Okay, I've drawn it out so that you can visually see it, but all you had to say was that less diffraction occurs. Okay, so you get less spreading out. In part C, this was done very well actually, so well done. You've got a path of red light. It's a ray travelling in, hits a prism. I've drawn the normal line on. It's more dense, so therefore it's coming in towards the normal here. And then it hits the second boundary. This is less dense, and it's going to continue on. You've got your two normal lines. We can see hopefully that green light, if I write out my order of the rainbow, is going to refract more than red. Okay, so I'm going to see more bending occurring. So this line needs to be lower down, and then again it continues to spread out as it enters the air on the other side. So you get 1 mark for this ray and 1 mark for this ray. Okay, number 8. So we've got an incomplete electrical circuit. A student completes the circuit and measures the current in the 6 ohm resistor. So let's think about the fact that current comes out of the cell, positive and negative, comes round. It will pass through AB. We'll consider what's there in a second. Current splits at a junction. So the current going in will split here, but it will recombine and then travel through the 6 ohm resistor. Okay, so because it asks you to draw an ammeter in one gap so that it can measure the current through here, we cannot place the ammeter on either of these branches because the current hasn't recombined before it gets into the 6 there. So the ammeter has to go between AB. And therefore I just need to close these gaps. Okay, these should just be straight lines so that I've got a complete circuit. A voltmeter is connected to measure the voltage across the 4 ohm resistor. Voltmeters are always connected in parallel, so we go one side and the other side of the thing we're trying to measure, and we connect the voltmeter across that. part I was a bit tricky, so we'll take it slow. It was worth 4 marks. Let's have a little look. Let's see if I can get everything in the screen. So, when the circuit is completed, the current in the 2 ohm resistor here is 2.5 amps. Calculate the current in the 6 ohm resistor. Well, we know that the voltage across the 2 ohm resistor will equal the voltage across the 4 ohm resistor, okay, because they're in parallel with each other. And remember that the voltage gets split across this bit and then this bit. Okay, so depending on whether the electron goes up through the 2 or down through the 4, it will drop the same voltage across there. So the first thing I did was I said, okay, well, the voltage across the 2 ohm resistor will be equal to the current through it multiplied by the resistance. V equals IR. So 2.5 amps, which is what we were told goes through here, multiplied by R, which is 2, means that 5 volts must have been dropped across the 2 ohm resistor, which also therefore tells us that this voltage drop on this voltmeter must also be 5 volts. And that must be equal to the current going through multiplied by its resistance. Okay, so we know that that's equal to I multiplied by 4. So therefore, I is equal to 5 over 4. Okay, and that's what tells me that I have a current of 1.25 amps. Another way to think about it is the resistance is doubled, so it's doubly difficult to get through, so the current will be halved, and half of 2.5 is 1.25. So now I know what current is coming into the junction before it reaches the 6 ohm resistor, and I just add those two up. 2.5 plus 1.25 gives me 3.75 amps, and that gives me my answer. 9a, describe the movement of charge that causes an object to become positively charged. Well, for something to become positive, it needs to have lost negative. Electrons are removed from the object. You then have a negatively charged rod held over an uncharged metal sphere. Add some positive and negative signs to represent the movement of charge within the sphere when we bring the negatively charged rod close. They will count, the examiners will count that you have an equal number of positive and negatives because it is an uncharged sphere, so it's neutral over all. So positive must equal negative. Secondly, you have to have at least 3 positives and 3 negatives for your diagram to be considered good. Okay, so positives don't move, they're equally distributed. So I've just equally distributed 5 positive charges. Then I know that I've got a negatively charged rod, so these electrons are actually going to move as far away as possible and come down here. Sorry, I drew this very late last night, I clearly didn't read very carefully. So what you will end up with is positives distributed and negatives moving down away from the negatively charged rod. Describe the actions in part II that must be taken to obtain an even distribution of positive charge on the surface of the sphere. Okay, so at the moment we've got a region that's negative and a region that's positive. And what we're saying is, what can we do to make the whole thing positive again? So the bottom needs to now become positive. So we connect this sphere to Earth. Okay, that will allow electrons to move down. Okay, leaving this no longer net negative. We then take this wire away so that we've now changed the distribution, and then we remove the rod. Okay, so we connect the sphere to Earth, we remove the connection, and then we remove the nearby negatively charged rod. Okay, 10. A radiation detector is placed on the bench in a lab. It detects a background count rate of 40 counts per minute. State what is meant by background radiation. Well, it's just radiation that is always present in the environment. Sources can be cosmic background rays, the sun, food, rocks, radon gas. You could have come up with lots. You could have said nuclear waste. Many things there for options. 1 mark for what it is, 1 mark for an example. a sample containing atoms of the radioactive isotope polonium-208 is removed, and it's brought close to the detector, and the average count rate increases to 890. So all of a sudden, instead of just the 40 counts per minute of background radiation, we've got a huge count rate because we've got a very radioactive source. We now bring 2 pieces of paper between the sample, which is emitting, and the detector, which is trying to pick up these radiation emissions. So the paper reduces the detector reading to 40 counts a minute again, which we know is 40 equal to the background radiation. So anything that was emitted from the source must be being blocked by the piece of paper, and the only thing that's reaching the detector is what was already in the background anyway. So it says deduce the type of radiation emitted. Well, it must be alpha. Alpha is the only radioactive emission that is completely stopped by paper. Beta and gamma can get through paper. Okay, so I get 1 mark for noticing that it must be alpha, and 1 mark for noticing that the reason for that is that all of it has been completely stopped. Then it asks for 3 marks for you to write the decay equation. So this is my alpha particle, which is a helium nucleus. 2 protons and 2 neutrons makes 4 nucleons, 2 protons. I get 1 mark for identifying this bit, and I then get 1 mark for my numbers being correct each. Okay, so 204 plus 4 makes 208. 82 plus 2 makes 84. 1 mark for each there. We're almost there. I think we've got 2 questions to go, I hope. Maybe 3. So, a student investigates a radioactive substance in a lab. You've got the count rate detected as the substance decays for 7.5 minutes. The background is 20 counts per minute. Please determine the half-life of the substance. Well, initially, the count rate is 220. But we know that 20 of those came from the background, so the source is actually emitting 200 counts per minute. After 1 half-life, that number will half to 100, but the detector will still pick up the background, so we have to add that number back on, and the detector will be picking up 120 counts per minute after a half-life. We then plot where 120 is, and we see that that occurs at 2.4 minutes. Then it says calculate the count rate detected at 9.6 minutes. Well, if the half-life is 2.4 minutes, 9.6 minutes is 4 half-lives. Okay, so the count rate will have halved 4 times. So it will have gone from 200 to 100, then to 50, then to 25, and then to 12.5. That gets you 1 mark. But the detected count rate needs to account for the background, which we know is 20, so we add 20 to it, and the total count rate will be 32.5. In B, the substance emits alpha particles and gamma rays. The student suggests that it is safe to store the substance in a plastic container that is only 2 millimeters thick. Is the student correct that it's safe to store? Well, no. Incorrect. 1 mark. Alpha will be blocked because it's blocked by air or paper, so plastic is certainly going to do the job. 1 mark. But gamma needs a thick lead container. It will penetrate through the plastic. Okay, so 1 mark for the right statement, 2 marks for your explanation, 1 linking to alpha, 1 linking to gamma. 12. Mass is a scalar quantity. State another scalar quantity. You could have written many things here. These are some examples, but you would have got it right if you chose a correct scalar. Speed, distance, time, temperature, energy, etc. All scalars, anything without a direction. Force is a vector, so anything that also has a direction associated with it, so velocity, acceleration, momentum. That was done well, so well done on that one. In part B, a boat is floating on still water. The mass of the boat is 290,000 kilograms. A resultant force of 50 kilonewtons, don't forget to add your 1,000, acts on the boat. So the mass of the boat acts vertically down. The resultant force is going to be the thing that causes the acceleration. Okay, so acceleration is force divided by mass. The resultant force is the one that we plug in, which is 50,000, and the mass is 290,000. Pop it into your calculator and you get 0.17 meters per second squared. In part C, you can see, not to scale, we've got a boat travelling towards the riverbank. You can see the direction of the river current. This was a vector diagram. So here we go. We've got an incomplete vector diagram of the forces acting on the boat. Now this could have tripped you up because you're actually given the resultant force, not the two forces that caused the resultant. So the boat experiences a force from the current to the left, okay, and that's drawn on for you. If we go back to the picture, you can see that the engine is adding a force up to the right, okay, and that's the one that's missing from the diagram. And we know that those two together will produce the resultant. This is the tail, this is the top, this is the tail, this is the top. If we're top to tail, we close the triangle and the resultant is here. Okay, so this is the first bit that we draw in. The scale is found by measuring the length, which we're told is 80,000 newtons, and it's 4.2 centimetres across. So if 80,000 newtons is represented by 4.2 centimetres, I divide this by 4.2, and it tells me that 1 centimetre is roughly equivalent to 19,000 newtons. You had a bit of scope there because it was a bit of a weird scale from the way it was printed. So if you wrote something slightly different, that's absolutely fine. We've closed the vector triangle. We've measured the length to be 12.4 centimetres. And we know that every centimetre now is 19,000 newtons. So we multiply those together to get the overall magnitude of the force from the engine. And again, you had a little bit of scope because of your scale differences. Okay, but mine was 235,600 newtons. Now the very last bit on the paper is the bit that was done worst because you didn't read the question. Measure the angle between the direction of the current, which is horizontal, and the force from the engine, which you've just drawn on. Well, the angle between that is this one. Everyone chose to measure this angle. Okay, and that's why you got that question wrong, because you didn't read which bit it should be. So get your protractor out, remeasure, and I think that most of you did draw it correctly, to be fair, and it should be 110 degrees. We are done.